Hi everyone. In this video I'm going to be going over the heat of fusion lab, so I'll explain the background of the lab, the procedure, and I'll work through some sample data. So heat of fusion lab, specifically heat of fusion of ice. So we're looking to calculate the heat of fusion of ice. Now you might already know the value if you've been doing calculations, but we're going to try to figure it out with some very simple equipment, and it's a very quick and elegant lab. In about 10 minutes of data collection you can probably get within 10% of the actual value. So the basic idea behind this lab is we're going to take some ice and we're going to take some hot water and we're going to use the hot water to melt the ice. Basically put the ice in the hot water and it's going to melt. And we're going to be able to calculate how much energy went into the ice to figure out the joules per gram that was required to melt it. So let's go through the theory here. So heat of fusion, or latent heat of fusion, is LF. And if you think about which formula involves LF, it's formula D on the list, up, flat, up. The second one, flat. Q equals M times LF, right there. So in this context, LF is your latent heat of fusion. That's what we're trying to solve for. This is going to be the mass of ice that melts. I'll just say ice, M of ice. And this is heat, and that's going to be the heat that goes into the ice in order to melt it. Heat that goes into the ice. So as you can see, it's pretty simple. In order to find LF, all we need to do is measure the mass of the ice, easy, use a balance, and measure the heat that goes into the ice. Well, that's the tricky part because there's no way to directly measure heat. There's no heatometer. There's a thermometer, but that measures temperature, and as you know, temperature is different from heat. So the problem is we have no direct way to measure this heat. So we're going to do it in an indirect way. Remember I said before, we're going to take some hot water and add ice to it. Well, what's going to happen to the water as the ice melts? Well, it's going to cool down because the heat from this hot water is what's supplying the energy for the ice to melt. Now, what we can measure is the heat that's released by this water as it cools down. And we know the formula for that. It's formula C on that 5-part curve. Q equals mc2 delta T. That's the formula for the cooling down or the heating up of water. So sometimes I refer to this as the ice formula and the water formula. Now let's talk about what this is. This Q is heat, right? But in this context, it's the heat that's released by the water as it cools down. Picture a cup of hot water, you're dropping ice cubes into it, the water's cooling down, the water's cooling down, the water's cooling down. That heat is being released by the water. So this is heat released by, and I'll say in this case, it's hot water. So how are we going to figure that out? All right, you'll have your cup of hot water. We need the mass. Now this is the mass of the water. Notice, that's mass of ice. This is mass of water. It's two different masses in this lab. You got to keep track of them. So this will be mass of water times C2. That's a known value. We have to assume that we know C2. You can't do this lab if you don't know LF or C2. So C2 is 4.18 joules per gram degree Celsius. And delta T is going to be the change in temperature of the water. So you're going to get the starting temperature and the final temperature of the water. So the basic idea behind the calculations here is that we're going to use the mass of the water, C2 of the water, and delta T of the water to find the heat released by the hot water. But how's that going to help us up here? Here's the big assumption of this lab. We are assuming that whatever value you get for this Q can be plugged in for this Q. In other words, this Q equals that Q. Now what does this really mean? It means that the heat released by the hot water is equal to the heat that goes into the ice. Or in other words, all of the heat given off by this hot water goes one place and one place only, into the ice cubes. Nowhere else. Not into the air, not into the beaker, not into the bottom, the lab table, into nothing. Only into the ice. Now is that true? Of course not. I mean, I'm holding this and it's hot because it's absorbing heat. It's releasing heat. I can feel that the evaporation, the convection coming off of there. So this is not true, but it's an assumption that we have to make. Now we can help it out, and we're going to do that in a couple different ways. For example, instead of a beaker, we're going to use a styrofoam cup, because a styrofoam cup is a better insulator. It's a worse conductor than Pyrex, the glass. So a styrofoam cup is going to absorb less heat from the water than glass would. So this is helping our assumption be true because the cup is now absorbing less heat than it would. The worst possible cup you could use would be like a metal cup, because the metal cup would absorb even more heat. And remember, our assumption is that 100% of the hot water's heat goes into one place only, the ice, not into the surroundings. So anyway, we find Q, we assume that this heat released by the water equals the heat absorbed by the ice, and now we have the Q that we need. Because mass of ice is pretty simple, pretty straightforward, and we multiply that by, to solve for LF, you divide Q by M. Basically, you get this by itself. So let me just talk through the procedure. I'm not going to write the whole procedure out here. But the basic idea is we need to find all of these variables. The one thing we didn't really talk about is how we find mass of the ice. Because let's say I intend on using this much ice here. How do I find the mass of that? Well, if you put it on a balance one at a time, it's going to start melting. We've seen how quickly metal melts ice because metal is such a good conductor. So that's not going to be very good because it's going to start melting it too early. I also don't want to put all of it on a balance and just find the initial mass of the ice now and then slowly add it. Because by the time you add all of this, and you're going to do it one piece at a time, a lot of it's going to start melting. You're not going to add that water, so the mass isn't going to match. So the way we're going to do this is measure the starting mass of your cup of hot water. Just get the starting mass, and then you're going to be adding ice cubes during the lab, and at the end you're going to find the final mass. Now what should the mass do afterwards? Well, it should go up because you're adding ice cubes, and those ice cubes melt, and basically the difference in mass is going to be your mass of ice. For example, let's say you have water here, hot water, and let's say this has a mass of 60 grams, and you add ice, you add ice, you add ice, and then at the end of the lab this has a mass of 90 grams. So it went from 60 to 90. What's the mass of ice you added? 30. So that's the basic idea there. So just running through this again, you get your cup of hot water. You need to find the mass of the hot water. I'll make up some sample data here too, and then we'll run through it. You're going to get your mass of hot water. Let's assume that we have 63.27 grams of hot water. Okay. You also need your starting temperature of the water, which we're going to get using a thermometer. Okay. So let's say that this has a starting temperature of the water 54.7 degrees Celsius. Okay. And now you're going to start adding ice to it. So you're adding ice, and you're stirring not with the thermometer, but with a glass stir rod. Okay. Now this question came up too. I prefer using metal stir rods because glass stir rods are much more susceptible to breaking. But think about why a glass stir rod would be better for this lab than a metal stir rod. Think about that assumption. Well, a metal stir rod is going to absorb more of the hot water's heat than a glass stir rod. So we're going to use the glass stir rod because it's going to absorb less heat. I mean, what would be the ideal stir rod? Probably like a styrofoam stir rod, you know? If I took like a strip of styrofoam from another cup and used that, that'd be even better. So you're adding ice and you're stirring. You keep adding ice and you keep stirring, and you do this for about 5 or 10 minutes, and you track the temperature, and once the temperature gets somewhere near 0, we're going to stop. So let's say our final temperature is 3.9 degrees Celsius. Now, it doesn't really matter how far you take it down. All we care about is delta T. Okay. Now we're going to find our final mass. Okay. Now the mass should have gone up, not because these are sitting in it. Obviously, you're going to take those out. But the mass should have gone up because we were melting ice in here. So there's more H2O in here than there was before. So let's say the final mass is 102.31 grams. Okay? And using just this data, we can now solve for LF. So let's run through that real quick. So remember, there are two formulas. There's Q equals M times LF, which is like the ice formula, and there's Q equals mc2 delta T, which is the water formula. Now we're looking to solve for LF in the ice formula, but we can't do it directly. We have to start with the water formula. We have to figure out Q of the water formula, or in other words, how much heat was given off by our hot water during this lab. Let's do that very quickly. Q equals the mass of the water. Notice there's a lot of masses here. This is going to be the mass of the water, which is right here, 63.27 grams. C2, that's the C value of water, 4.18 joules per gram degree Celsius. I'm running out of room here, so I'll just squeeze that in there. Delta T, 54.7 minus 3.9. What's that? 50.2? 54.7 minus 3.9, 50.8 degrees Celsius. Yeah. Okay, so we multiply these together, and you can round off sig figs now, or you can just do it at the end. I'll do my sig figs at the end. So Q equals 13,435 joules. That's the amount of heat that left my hot water as it cooled down. The big assumption of this lab is that 100% of these joules went where? Into the ice, and only the ice. So now we can plug this Q value into that Q value. M, this is the M of the ice. How do we get the mass of the ice? Notice, nowhere it says mass of ice. Well, the water started at 63, it ended at 102. The difference there is going to be the mass of ice. So 102.31 minus 63.27 gives us 39.04 grams, and that's our mass of ice. So we are looking to solve for LF. I'll do this in over here. My formula, Q equals M times LF. To get LF by itself, we divide M out of there. So LF equals Q over M. That's my formula. LF equals Q is 13,435. And include your units. That's joules. M is the mass of the ice, which is 39.04 grams. So look at the units. Does anything cancel? No. And that makes perfect sense because the unit for latent heat of fusion is joules per gram. It's the amount of heat per gram of material. So 13,435 divided by 39.04 gives, well, I picked good numbers. 344, and let's check our sig figs now. So I'm seeing two sig figs here, but we never actually used 3.9 in the multiplication or division. We used delta T, which was 50.8. So I'm seeing 3 sig figs here, 4 here. So 3 sig figs is correct. 344 joules per gram, which is close to the theoretical value, which is 334. And then you could work out a percent error from this as well. So that explains the lab. Again, simple, elegant lab using very simple materials. You can get really close to the LF value.